So in this video, I am going to explain about what is red black tree. Before that, I think you have already aware of the binary tree, binary search tree and AVL tree. This is red black tree. So a binary tree is nothing but a node is having 0, 1 and 2 children. Binary search tree, it means that the left children will be less than equal to root and right children will be the greater than root. AVL tree is saying that each and every node balance factor should be 1, minus 1 and 1. This will be the 0, 1 and minus 1. If it is in this range, then only we can say that AVL tree. AVL tree is going to follow this 3 property. AVL tree will follow this 3 property. Binary tree as well as binary search tree property and their own property. This 3 property is following. Red black tree. Red black tree is also binary search tree. Red black tree is also following the binary tree property, binary search tree property and as well as their own property. And their own property is that it's working on the color bit. Right? So why red black tree? Why not AVL tree? Why? What's the reason of that? Why we were using red black tree? We'll see that what is the reason why we came for the red black tree. If it is AVL tree is also self-balancing. AVL tree is also balanced binary search tree. It's reducing the time complexity order of log n because of that balanced tree. So then why you are using red black tree? The reason is that AVL tree is having so many rotation like left LL rotation, LR rotation, RL rotation, RR rotation. So there are so many rotation you are performing when you construct the AVL tree. When you construct the AVL tree or insertion of the node and deletion of the node, what happen is that if it is a large number of data, if you are using AVL tree for insertion and deletion, what happen is that if it is violation occur, you will going to perform so many rotation and that is expensive. That's expensive because every rotation will take some time. So that's some cost. So because of that reason, the insertion and deletion is taking more number of rotation, and because of that reason it will be some expensive. It's expensive and costly. Because of that reason, red black tree we use. Red black trees is having less number of rotation. Red black tree is having less number of rotation and that's why we were using. So if we say that for the searching purpose, if I say that searching purpose, that AVL tree is more preferable if we are searching the element, because red black tree is not strictly balanced. It's just a balanced binary search tree, but it's not strictly balanced binary search tree. So for the searching purpose we prefer AVL tree, but for the insertion and deletion purpose we prefer the red black tree. Because in red black tree less number of rotation, but in AVL tree is having rotation issue. Because of that we were using red black tree. Right? So this is the reason behind that to learning about the red black tree. Now we'll see that what is the red black tree. So red black tree is also kind of self-balancing binary search tree. It's also balanced one, but it's not strictly balanced, but it's roughly balanced binary search tree, where each node has an extra bit. What is this extra bit? Extra bit is that if you want to store red black tree in the memory, you are going to use one extra bit. Normally, if it is normal tree, you are just using that left child, right child and data. There is a 3 pointer, left child and right child and data. This was the representation of the normal tree. But if you are going to represent the red black tree, you will going to use that left children and one bit. This bit is nothing but this may be 0 or maybe 1. 0 it means that you will that will be black and 1 will be the red, and this is the data part and this is the right children. So you have a two pointer and one extra bit and that the data. So this bit is used to represent the color. That's what this is the way of representing the red black tree in the memory. Now, so this extra bit is just interpreted as a color. So this is the red black tree. Red black tree is nothing but it's a binary search tree, but it's using one extra bit that's interpreted as a color. Now one more thing is that here in the red black tree, so far we have learned that leaf node means a node is having 0 children. Yes, this is here also same thing, leaf node is the 0 children, but red black tree is also considering that a node is having leaf node means in 0 children, that there will be no left children, no right children. So you just for the sake of the representation you just create it as a null. So this is 11 is the leaf node. 11 is the leaf node. There is no left children and right children. So this is null. You just put it that a null. Left children will be null. Right children will be null, and their color will be the black. So always whatever the leaf node, their left children and right children will be the null or nil. Whatever you want to say, that null or nil both is same. There is nothing. It means that nothing, and their color will be the black. So just if 11 is the leaf node, so their color is black, and 15th is the leaf node, there is no left and no right. So just simply I have assumed that null. Null means nothing, and simply have just for the sake for the representation just I have created. So this is the one way, either you have to separately create left node, right node, and that will be the null, that you do that. And another way, you simply create single null, and you just connect that their left children and right children both will going to point to the nil, and similar like this you can do that. Now this is all about the red black tree. Now we'll see that the property of the red black tree, and we'll check that some example that is it valid red black tree or not valid. So coming to the property of the red black tree, so there are total 6 properties here in the red black tree. One property is saying that the red black tree must be binary search tree. This is very much important. If it is tree is not a binary search tree, you directly say that that's also not a red black tree. Second property is saying that root must be black color. Root is also black color. If it is root is not black color, you can also say that that's not a red black tree. And third property is saying that the children of the red color node must be black. The whatever the red color node, their children should be black. And also saying that there should not be 2 consecutive red. 2 consecutive red is not possible. So these are the 3 property. Fourth property is saying that in all the path of the tree, there should be same number of black colored node. This is the fourth. Fifth property is saying that every new node must be inserted with a red color. So this property is useful for the insertion part. When you insert element, that time this is going to use. So for now, you just keep it. And sixth one is saying that every leaf null node, do remember leaf null node, it means that whatever the leaf node, and they have leaf node is no children, so their left and right will be the null, that must be black color. That must be black colored. Okay, so now these are the property. Now we'll check that each and every example which tree is valid and which tree is not valid. Now we'll be going to check that each and every property, which property is following, which property is not following, that we will going to check one by one. So now for this tree, we'll check that is it first property is check that what is the first property, the tree must be binary search tree. So come for this check that 30 is less than 60 is greater than 20 is less than 30, yes. 55 is less than 60, 65 is greater than, yes. So first property is followed. Second property is saying that root node must be black colored. So what is the root here? Root is 50. The root color is here red, but the property is saying that root node must be black color, but here is the red. It means that this is not a valid red black tree. This is not a valid red black tree. So if it is second property is violating, it's not required to check the remaining property. You can directly say that this is violating the property and this is not a valid red black tree, right? So next coming to the next tree, we'll check that is it following all 6 property or not. So first property saying that tree must be the binary search tree. So first check that 30 is lesser than, yes. 60 greater than, yes. 20 is lesser than 30, yes. 35 is greater than 30. 65 is greater than 60, yes. This is binary search tree. So first property is done. Second property, root must be black colored, yes. Root is black color, yes. So must color. So 2 is also following. Third, the children of the red colored node. Where is the red color node? This is the red colored node. Their children is 20 and 35. Both is black color. Yes, this is also following. This is the next red color 65. 65 children is null null, and that is both color is black. So third property is also following. Now coming to the fourth property. Fourth property is saying the path of the tree. All path, here it's not saying the single path, in all the path of the tree there should be same number of black colored node. One more thing is that fourth property is saying the path. How you know that the path, what is the path? How many null node here, that many path is there in the tree. So how many null node? 1 2 3 4 5 6 7. So total 7 nil node is here. Total 7 nil node here. It means that total 7 path is here. Total 7 path is here. So you check that one by one and check that how many black node in each and every path, because here saying that in all the path the black color node should be same. They are asking that the black color node should be same in all the path, then only the fourth property is going to satisfy, right? So we'll check that. So this is the nil, first nil. So I will check that one black, here not black, so 1, here 1 only, here 2, and this is 3. So in first path the 3 black node. Coming to the second path, 1 black node, 0 means 1 1, and here 2, and this is 3. Yes, second path is also having 3 black node. Third path will check that one black node, here not there, here 2, and this is 3. Next one, this is also following 3. Okay, 1 not considered, 2, and this is 3. So here also 3. Now coming to the right part, now we'll check that 1 black node, 2 black node, 3 black node, right? So this one also you have to check that. Okay, so 3 black node. Now coming to this path, 1 2, this is not considered, this is 3. Yes, now one more path is there, 1 2, and this is not there, and this is 3. Means all these path is having 3 black nodes. So fourth is also satisfied. Fifth, for now you ignore it. When you insert the element, that time it is going to use. Coming to the sixth, every leaf node or null node must be colored black. Look at that, all the leaf node, null node, all these are black. Yes, all these are black. It means that this tree is following all sixth property. It means that this is the valid red black tree. Valid red black tree. Understood? So this is valid red black tree. Now we'll check the another one, and that's the exceptional one, and that's very much important. So try to understand this. So this is my tree. Name is saying that red black tree, but in this tree there is no red. So don't be confused that red is not there. So don't directly say that this is not a red black tree. Don't directly say. First you have to check that all the property of the tree it is following or not. If it is not following, then you say that not valid. If it is following, you can say that this is a valid red black tree. Even red color is not there also. Right? So now we'll check one by one property. So first property is saying that a tree should be the binary search tree. So look at that, 50 less than 30 less than 50, yes, 60 greater than 50, 20 less than 30, 37 greater than 65 greater than. Okay, so first is done. Second is saying that root must be black colored. So root is already black, so okay, second is also done. Third is saying that the red colored node. So here there is no red color, so third is also following. Fourth is saying that in all the path, the black colored nodes should be same. So now we'll check that how many path it is. 1 path, 2 path, 3 path, 4, 5, 6, 7 path. Now we'll check that all 7 path is having same number of black node or not. So 1 black node, 2 black node, 3 node, 4 node. So this path is having 4 black node. Now check that 1, 2, 3 and 4. So this path is also having 4. Now check that another 1, 2, 3 and 4. This path is also having 4 black node. Now we'll check another 1, 2, 3, 4. This is also having 4. Now check another 1, 2, 3. Look at that. Here there is a 3 black node, but remaining is having 4. It means that's violating the red black tree property. So this is not a valid red black tree. Reason is that this path is having only 3 black node, 1, 50 is 1, 60 is 1, and this null is 1. So total 3 black node, but remaining is having 4 black nodes. So this is not valid. This is not valid binary red black tree. So this is not valid red black tree. I hope you understood. Now I will check that another. I will check another. See here all these node was the black, right? Now I will going to explain the another one. I'll check that here all these properties following or not. First property is that is red black tree is binary search tree. Yes, this is a binary search tree. 50, 30 is less than 50, yes. 60 is greater than 50, yes. 20 is less than 30, yes. 37 greater than 57, less than 60, yes. So 65 is greater than. Okay, fine. Here I have connected all these leaf node null is in a single null because there was no space, so I have taken and I have connected. Okay, fine. Now we'll check that second property. Root must be the black colored. Yes, root is black colored, so second property is also satisfied. Third property is saying that the children of the red colored node must be black. So here there is no children red color, so not required to check. Third is also following. Coming to the fourth property. In all the path of the tree, there should be same number of black colored node. Now we have how many path? 1 path, 2 path, 3 path, 4, 5, 6, 7, 8 path. Total 8 path you have to check. Okay, 1 black node, 2 black node, 3 black node, and this is 4 black node. Yes, so single path you have checked 50, 20, 30 and their left children. Okay, next you have checked that 50, 30, 20 and then right. So 1, 2, 3 and 4. Here also 4 paths. Now check that 50, 30, 17 and then left. 1 black, 2 black, 3 black and left is 4th. This path is also having 4. Coming to the next, 1 black, 2 black, 3 black and right also 4. Now next you check that 50, 60 and 57 and their left. 1 black, 2 black, 3 black and 4 black. Yes, this path is also having 4. Now check that 50, 60, 57 and right. 1 black, 2 black, 3 black and 4 black. So this path is also having 4. Now 50, 60, 65 and their left. 1 black, 2 black, 3 black and left is also 1 black. So total 4. Coming to the right side. So 50 black, 1 black, 60 1 black, 65 1 black and right children also 1 black. So means in all 8 path is having 4 red black and all path is having equal number of red black tree, right? Fifth one is not required. Sixth one is saying that every leaf node or null node must be colored black. So look at that, all these are the black, all these are black. It means that this tree is following all the property of the red black tree. It means that this is the valid red black tree. This is the valid red black tree. And one more thing you observe that, and that's very much important. Just give me 1 minute, just I'll erase it for the better understanding. You have seen here all these properties satisfying. Now one more thing you try to observe here is that all these node is here is black node. All these node is here black node, and one more thing is that you try to observe it here which tree it is. It's a perfect binary tree. So perfect binary search tree means every node is having here is 2 children and all these node at all the leaf node at same level, and this concept is called perfect binary search tree. So there is one important point is here, if a tree is a perfect binary search tree and all the node color is black, if the binary search tree is a perfect binary search tree and all the node color is black, then you can say that that's the valid red black tree. Do remember, if it is a perfect binary tree and all the node color is black, then only you can say that this is the valid red black tree, right? Look at here, this is also all node color is black, but still this is not a valid red black tree. Reason is that this is not the perfect binary search tree. This is not a perfect binary search tree. Because of that reason it was not valid, but this is valid binary search tree, right? Now coming to the another, this is the tree. Now we'll check that it's this binary search tree. 50, 30 is lesser than, yes. 20 is lesser than, yes. 37 is greater than 30, 60 is greater than. Okay, fine. So this is first property is true. Second property, root must be colored black. Okay, second property is also satisfied. Third property, the root children of the red colored node must be colored black. Children of the red colored node, children must be colored black, and there what it is saying that there should be not two consecutive red node. Two consecutive red node is not possible in the red black tree, but here if you see here there is a two consecutive node is red here, and that's impossible. Red black tree is not allowing you to use two consecutive node be colored will be red. So this is the violating the property. So this is not a valid red black tree. If it is one property is violated, not required to check other property. Directly you can say that this is not a valid red black tree. So this is all about red black tree and their property, and I have given some example and I explained that how you tell that valid red black tree and how you say that not valid red black tree. So next video I am going to explain about the insertion operation, or we can say that how to construct the red black tree and how to, if it is violate the property, then how to maintain that property, how to make that valid red black tree. So that's all about that red black tree. Thank you for watching my video.